Okay, today we're going to talk about limiting reactions. So, first off, this is no different than any other stoichiometry reaction. The only thing we're going to do is we're going to find out which one of the two reactants are going to limit the reaction that's going to happen. So when we start talking about limiting the reaction, this limiting reactant is the one that's going to run out. It's the one you're going to be short on. We don't really want to have a reaction where we're going to have that. So just think about this. If you're going to bake chocolate chip cookies, you're going to go to the store, you don't have anything in your house, you got to buy every single ingredient. One of the ingredients you're going to buy is a bag of chocolate chips. The other ingredient that you have to buy is a bag of flour. Now, if you put that whole bag of flour in your cookies with that bag of chocolate chips, your cookies are going to taste awful. You don't want to use the whole bag of flour. But you're going to use the whole bag of chocolate chips. The chocolate chip is what we consider the limiting reactant. It's the one that's going to run out. The flour that we're going to have, that whole bag, which we don't need to use the whole bag, is going to be excess, and we're going to have leftover of that. So we're going to determine which reactant is going to be the excess and going to be the limiting. So first off, we want to start off with a balanced chemical equation. Oops, too far. So let's balance this chemical equation. No, it's not balanced quite yet. We need to put a 6 here and a 2 in front of the iron. So now we have a balanced chemical equation. Now they gave us some things, so let's look what they gave us right here. So we have 100 grams of sodium and 100 grams of iron oxide. We don't know which one is going to be the limiting, so we have to determine that. First off, we need to use the balanced chemical equation. So in order to use the balanced chemical equation, we need to convert the grams that were given to us down here into moles. So let's do that. So let's take 100 grams of Na and convert that into moles of Na. Then we can kind of compare using a molar ratio which one is going to run out and which one is not going to run out. So in this case, we have 4.3 moles of sodium. And let's do the same thing with our iron oxide. 1 mole of, Fe2O3. Again, all I'm doing is converting this into a mole. And we get 0.63 moles of Fe2O3. Okay, so now that we have this both converted into moles, so step 1's done, we converted them into moles. Now we can look at our balanced chemical equation and see if we have the right ratio. So we want to make a proportion for this. So what that means is we know that in the balanced chemical equation, 6 moles of Na is equal to 1 mole of Fe2O3. We know those are equal. Now, knowing that they're equal, we can set this to the opposite side using just one of these two. So we just want to use one of these. We don't want to use both of them. We want to use one. So let's just use iron oxide. So we're going to put 0.63 moles of Fe2O3. Instead of putting our 4.3 up here, we're going to put X moles of Na. And we're going to solve for this X. The reason that we're solving for this X is we want to find out, hey, do we have more moles of this or do we have less moles? So when we solve for X, X is going to be equal to 3.78 moles of sodium. So if we have 6.3 moles of iron oxide, we need 3.78 moles of sodium. That would be a perfect 6-to-1 ratio for this compound. However, if we look over here, what do we got? We have this. We have 4.3 moles of sodium. Well, obviously 4.3 is more than 3.78, and so sodium would be our excess. Now, if we did this the opposite way, where we put moles of sodium on the top here, instead of our 6.3, and our 6.3 became our X, you're going to find out that this number here would be much larger than this. Because we don't have that number, that would be not enough of that substance, so it would limit our reaction. And so you could do it either way. It doesn't matter. But in the case that we have, we know that this is going to be our limiting, and we got our excess here as well. So this sodium is going to be our excess. So now let's go down and answer some of these questions that we have down here on this. All right. So our limiting reactant is going to be our Fe2O3, and our excess reactant is going to be sodium because we had more moles of sodium than what we actually needed. So now we have to find the mass of the solid iron product. So here's the big key for this. If we have two masses that we started with, which one do we want to use? Well, it's like baking cookies. Trying to figure out how many dozen of cookies you're going to bake, but you only have one bag of chocolate chips. You don't want to use the bag of flour to determine how many chocolate chip cookies you're going to make, because they're not going to be very chocolatey. So we want to go with the one that's limiting. So we always use the limiting to determine the mass of anything. In this case, we don't have to start with 100 grams. You can if you want to, but we already solved this for moles. So we're going to start with moles. So we know we have 0.63 moles of Fe2O3. We don't have to go back and do grams. If you want to do a mass to mass, you can, but you don't have to. You've already done that step. So now we're going to convert that into grams of iron, our product. So we have to use the molar ratio. So we know 1 mole of Fe2O3, I'm getting this from the balanced chemical equation, is equal to 2 moles of iron. Okay, so now we got to the mole part. Now we need to go to grams. So here and here canceled out. So now we need to go 1 mole, so we're going to use the molar mass, grams per mole, of iron is equal to 55.8 grams of Fe. We solve for this, you get 70.308 grams of iron. So that's how much iron is produced from this. Again, you have to use the limiting because it's the one that's going to run out. You don't want to use the one that you have excess of. That's just silly. You'll get the wrong deal. So now, what is the mass of the excess reactant that remains after the reaction? So our excess reactant was sodium. So we're going to go to grams of sodium using our limiting. Again, you got to use the thing that limits the reaction. So we have moles of Fe2O3, and we're going to convert that into grams. So using the molar ratio, 1 mole of Fe2O3 is equal to 6 moles of Na. We're going to convert this now into grams. Cancel these labels. 1 mole of Na is equal to 23 grams of Na. Multiply the top, divide it by the bottom. That shouldn't be too hard. And we get 86.94 grams of sodium. This is needed. This would be like the amount of flour that we would have needed for the reaction. We don't need the whole bag. We just need a portion of it. So to figure out how much we have left, or how much excess remains after the reaction, we take what we started with. Well, we started with 100 grams. We subtract that from what we needed, which was 86.94. And we get a difference of 13.06 grams of Na remain. And this sodium can be used to do another reaction somewhere. So again, we always start with a balanced chemical equation, and from there we can go and convert grams to moles. So let's do another one. This is a photosynthesis reaction. Hope that you guys know the balanced chemical equation for photosynthesis. Done it a lot. So we have 6 CO2 plus 6 H2O produces glucose, C6H12O6 plus 6 O2. Okay, so our first step, we are given grams of 2 reactants. We have to figure out which one is going to be limiting. Don't just assume one's bigger, so that has to be limiting. Determine. So we have 88 grams of CO2. We're going to convert that into moles. So 1 mole of CO2, 44 grams of CO2. We get 2 moles of CO2. So let's do moles of water. So we have 64 grams of H2O, and we're going